September 12, 1944. 28,000 feet above Schweinfurt, Germany. First Lieutenant Robert Morgan pressed his eye to the Norden bomb sight mounted in the nose of his B-17, watching German factories crawl across the crosshairs. The device beneath his hands represented America's most closely guarded secret, a mechanical computer worth more than the bomber carrying it, protected by armed guards, classified beyond even radar technology. Army Air Force's briefings had promised pickle barrel accuracy from 5 miles high. Place a bomb in a barrel from 25,000 feet, they said. Strategic bombing would win the war through precision strikes on Germany's industrial heart. The reality appeared in Morgan's bomb sight optics as scattered impact points across the target zone. Of 36 bombers releasing over the primary target, perhaps 8 placed ordnance within 1,000 feet of the aim point, not the 300-foot circular error briefed in England. Ground haze, flak bursts, and defensive maneuvers disrupted the careful calculations. The Norden could compute altitude, airspeed, drift, and ballistics with unprecedented accuracy. It could not account for human fear, mechanical failure, or combat chaos. The device cost $8,000 per unit, equivalent to a house in 1944 dollars. The United States produced over 50,000 of them, trained 50,000 bombardiers in their use, and built an entire strategic doctrine around their promised precision. The question became operational. If technology promised accuracy, why did bombs scatter across German countryside? The answer lay not in the machine's mathematics, but in the gap between laboratory perfection and combat reality. The story of America's most secret weapon began more than a decade earlier, rooted in a strategic vision that rejected the indiscriminate destruction already consuming European cities. American military planners in the early 1930s faced a fundamental dilemma: how to strike enemy industry without obliterating civilian populations. How to destroy ball-bearing factories without leveling entire neighborhoods. British doctrine increasingly favored area bombing saturation attacks that made no distinction between military targets and residential districts. American thinking moved in the opposite direction, toward precision strikes that promised moral superiority alongside military effectiveness. Major Hugh Kinnear reviewed procurement specifications at Wright Field in Dayton, Ohio, during the winter of 1933. The Air Corps Materiel Division document before him outlined requirements for an optical bomb sight capable of hitting targets with unprecedented accuracy. Circular error probable of 300 feet from 20,000 feet altitude. Existing bomb sights fell far short of such performance. The British Mark 7 sight achieved 1,000-foot accuracy under perfect conditions. French and German sights managed little better. Kinnear's specifications demanded revolutionary improvement accuracy 3 times better than anything flying anywhere in the world. The requirement reflected broader strategic thinking within the Army Air Corps. Brigadier General Billy Mitchell had spent years advocating for strategic bombing as decisive warfare attacking an enemy's industrial capacity rather than engaging armies directly. Mitchell's vision promised to end wars faster and cheaper than traditional ground campaigns, but the theory required precision that contemporary technology could not deliver. Drop bombs from 4 miles high using sites designed for the Great War, and ordnance scattered across square miles. The gap between doctrine and capability demanded technological breakthrough, not incremental improvement. Carl Norden emerged as the man to bridge that gap. A Dutch-born engineer who had emigrated to America at the turn of the century, Norden had spent 15 years perfecting gyroscopic stabilization systems for naval gunnery. His Mark III bomb sight, tested by the Navy in the early 20s, demonstrated superior accuracy to competing designs, though it remained complex, expensive, and temperamental. The Air Corps approached him with specifications that seemed almost impossible: automatic compensation for altitude, airspeed, wind drift, and ballistic trajectory, gyroscopic stabilization, immune to aircraft vibration, mechanical computation, accurate within seconds of arc, construction suitable for mass production and combat durability. Norden accepted with characteristic confidence, promising delivery within 2 years. Development consumed far longer. His perfectionism drove endless refinement of mechanical components, optical elements, and stabilization systems. Each subsystem required precision manufacturing beyond standard industrial practice. Gear trains demanded tolerances measured in 10,000ths of an inch. Optical components needed grinding and polishing to laboratory standards. Gyroscopes required balancing so precise that temperature variations measurably affected performance. The device became an obsession. Norden personally supervised production of critical components, rejected batches for microscopic flaws, and redesigned mechanisms that failed to meet his exacting standards. Prototype testing revealed both extraordinary promise and significant limitations. Test bombardiers achieved 200-foot accuracy from 15,000 feet under ideal conditions: calm air, clear visibility, no defensive fire, unlimited time for setup and calculation. The results validated Norden's fundamental design, while highlighting the chasm between controlled testing and combat reality. Under laboratory conditions, the bomb sight performed miracles. Whether it could deliver similar performance while German fighters attacked and anti-aircraft shells burst nearby remained an open question. The device operated through elegant mechanical computation that would have seemed miraculous to bombardiers of the previous war. The bombardier input, current altitude, airspeed, and estimated wind velocity through external knobs and dials. Internal mechanisms translated these inputs into continuous calculation of the bomb's trajectory. A stabilized gyroscope maintained absolute reference regardless of aircraft maneuvers. Optical elements provided magnified view of the target below. As the bomber approached the release point, the bombardier tracked the target through crosshairs, while the Norden automatically computed the precise instant for bomb release. The mathematics involved calculating the parabolic trajectory of a falling object while the aircraft traveled at 250 miles per hour through three-dimensional space would have required a trained mathematician minutes to solve on paper. The Norden solved them continuously, updating calculations 50 times per second through purely mechanical means. Production posed challenges nearly as complex as development. The Mark 15 bomb sight contained over 2,000 individual parts, many requiring machining to tolerances beyond standard manufacturing capability. Norden insisted on maintaining quality control personally, limiting production to a single facility, his own company's plant in New York. Through the mid-30s, output remained minimal, fewer than 50 units annually. The Air Corps, expanding rapidly as war clouds gathered over Europe, needed thousands of bomb sites for the bomber force under construction. The bottleneck threatened to render precision bombing doctrine purely theoretical. Industrial mobilization finally forced Norden to accept expanded production. Contracts went to multiple manufacturers, including Remington Rand, which established dedicated bomb sight production lines. Quality remained paramount. Each unit underwent rigorous testing before acceptance, and failure rates in early production ran above 20%. Workers assembled components in climate-controlled cleanrooms, using jeweler's tools and inspection equipment borrowed from watchmaking. A single speck of dust in the wrong location could throw off the gyroscope balance. A gear tooth, worn by a few micrometers, could introduce error into trajectory calculations. The precision required made each bomb sight a miniature marvel of mechanical engineering. The cost reflected such precision. At $8,000 per bomb sight, when a new B-17 bomber cost $238,000, the targeting device represented more than 3% of the aircraft's total value. For comparison, the bomber's 4 engines combined cost $44,000. The Norden cost nearly 1/5 as much as all 4 engines, a ratio that astonished critics and raised questions about whether such expensive equipment could justify its cost through improved accuracy. Security measures surrounding the Norden exceeded those for any other military technology of the era, rivaling even the secrecy that would later envelope the atomic bomb project. Armed guards accompanied every bomb site from factory to airbase. Storage facilities required multiple locks and constant surveillance. Bombardiers swore secrecy oaths before training, faced court-martial for discussing the device's operation, and carried orders to destroy their bomb sites if capture seemed imminent. Combat crews installed explosive charges connected to emergency switches, allowing instant destruction of the equipment. A thermite grenade mounted directly to the bomb site frame could melt the entire device into slag within seconds. The security obsession reflected genuine concern about technological advantage. Army Air Force's intelligence believed the Norden represented a 5-year lead over German and Japanese bomb site development. Loss of even a single intact unit might allow enemies to copy the design and eliminate American precision bombing superiority. Whether such fears reflected reality remained uncertain. Both Germany and Japan had competent optical engineers and sophisticated mechanical industries, but the perception drove absolute security protocols that treated the bomb site as more sensitive than top-secret radar systems, or even the early proximity fuse technology. Training programs matched the security emphasis in complexity and cost. The Army Air Forces established dedicated bombardier schools across the Southwest, where trainees spent months mastering the Norden's operation. Students learned the theoretical mathematics of ballistics, the practical mechanics of gyroscope stabilization, the optical principles of magnified sighting, and the manual procedures for input and adjustment. Early training used wooden mock-ups before students graduated to actual bomb sites in aircraft. Practice bombing runs over desert ranges consumed thousands of flying hours and tens of thousands of practice bombs. Instructors emphasized that bombardiers bore responsibility for mission success. Pilots merely positioned the aircraft. Navigators guided it to the target area, but the bombardier determined whether bombs struck enemy factories or empty fields. The phrase pickle barrel accuracy entered Air Force's vocabulary during these training programs, promising that skilled bombardiers could place bombs in a barrel from 25,000 feet. The boast had some basis in training range results. Under ideal southwestern conditions, clear skies, unlimited visibility, no opposition, calm winds, known altitude, bombardiers regularly achieved 300-foot accuracy. Some exceptional crews managed 200-foot circular error. These performances established the baseline expectation carried forward into combat planning. American strategic bombing would surgically remove enemy industrial capacity while sparing civilian lives. The doctrine rested entirely on the assumption that training range performance would translate to combat conditions. Nobody seriously questioned whether such precision could survive fighter attacks, anti-aircraft fire, bad weather, equipment malfunctions, and the psychological stress of men trying to kill you while you attempted delicate optical alignments and mathematical computations. The training produced confidence bordering on arrogance among bombardier graduates who believed their Norden bomb sites made them capable of precision that would astonish military historians. They would discover that combat imposed limitations no amount of training could overcome. The 8th Air Force arrived in England during summer 1942, bringing America's strategic bombing doctrine to the European theater for its first real test. While British Bomber Command conducted nighttime area raids that obliterated German cities, American commanders insisted on daylight precision bombing of specific industrial targets. The strategy required the Norden bomb site to perform exactly as advertised, delivering 300-foot accuracy from 25,000 feet, while German fighters attacked and anti-aircraft shells burst around the bombers. The divergence between American and British doctrine reflected not just different tactical approaches, but fundamentally different moral philosophies About warfare. The British had endured the Blitz, had watched their cities burn, had lost tens of thousands of civilians to indiscriminate bombing. They saw no reason to spare German civilians when Germans had shown no mercy to London. Americans, entering the war fresh and still clinging to pre-war moral certainties, believed precision bombing offered a more ethical path to victory. The first major test came on August 17, 1942, when 12 B-17 seconds attacked the Sotteville rail yards near Rouen, France. Bombardier First Lieutenant John Dowsett led the formation, his Norden tracking the rail junction through partly cloudy skies. The mission profile seemed almost ideal for demonstrating precision doctrine: a clear military target, relatively light defenses, experienced crews, good weather. Of the 36 500-pound bombs dropped, 22 struck within the target area, a success rate that impressed commanders and seemed to validate precision bombing doctrine. Intelligence photographs showed destroyed trackage and damaged rolling stock with minimal damage to surrounding neighborhoods. The mission entered Air Force's lore as proof that the Norden delivered on its promises, becoming Exhibit A in arguments that American methods surpassed British area bombing in both effectiveness and morality. Subsequent raids painted a more complex picture. Weather over northern Europe rarely matched the clear skies of American training ranges or even the relatively favorable conditions at Rouen. Cloud cover obscured targets more often than not, forcing bombers to bomb through clouds using radar approximation or abandon missions entirely. When visibility permitted visual bombing, German defenses disrupted the careful procedures that accuracy demanded. Flak bursts rocked bombers during bombing runs, throwing off the delicate gyroscopes that provided the Norden's reference baseline. Fighter attacks forced evasive maneuvers that made steady tracking impossible. The bomb site required the aircraft to fly straight and level for the final minute before release, exactly the conditions that made bombers most vulnerable to both fighters and anti-aircraft fire. Combat introduced variables that laboratory testing never anticipated. Even under attack-free conditions, the strain of combat affected bombardier performance in ways peacetime training never replicated. Men struggled with oxygen deprivation at high altitude, where even small errors in equipment or procedure could cause hypoxia that degraded judgment and motor control. Temperatures at 25,000 feet dropped to 40 degrees below zero, numbing fingers that needed to make precise adjustments to delicate controls. The fear of death concentrated the mind wonderfully, as Samuel Johnson observed, but it also made steady hands and calm calculation difficult for all but the most exceptional individuals. The mechanical perfection of the Norden could not compensate for these human and environmental factors. The device computed trajectories with extraordinary precision, but only if provided accurate inputs. Altitude had to be correct within a few hundred feet. Airspeed needed accuracy within 5 knots. Wind estimates had to approximate reality within 10 degrees of direction and 5 miles per hour of velocity. Any error in these inputs propagated through the trajectory calculations, producing corresponding errors in bomb placement. A bombardier who misestimated altitude by 500 feet would miss his target by 200 feet, even if everything else was perfect. Under combat stress, maintaining such precise inputs proved nearly impossible. The raid on Schweinfurt's ball-bearing factories in August 1943 demonstrated both the potential and limitations of precision bombing in stark terms. 230 B-17 seconds attacked the facilities that produced over 40% of Germany's ball bearings components, essential for aircraft engines, tank transmissions, and virtually all military machinery. 8th Air Force planners predicted that destroying Schweinfurt's factories would cripple German war production for months, possibly shortening the war by forcing Germany to negotiate from industrial weakness. The strategic logic seemed impeccable. Identify a choke point in enemy production. Apply precision bombing to eliminate that choke point. Watch enemy military capacity collapse. The mission encountered fierce resistance from the moment bombers crossed the German frontier. Luftwaffe fighters attacked in waves, pressing through bomber formations despite defensive fire. Messerschmitt, 109 seconds, and Focke-Wulf, 190 seconds, made repeated passes, forcing bombers into evasive maneuvers that disrupted bombing runs. Flak batteries around Schweinfurt, reinforced because German intelligence knew the factory's importance, created dense barrages through which bombers had to fly steady and level for accurate bombing. The contradiction proved unavoidable. Precision required steady flight, but steady flight meant maximum vulnerability to defenses. Of 230 bombers dispatched, 60 failed to return, a 26% loss rate that represented unsustainable attrition. The survivors claimed good bomb hits on the target factories, their bombardiers insisting that the Norden had functioned perfectly despite the chaos. Post-strike reconnaissance revealed a more sobering reality. Of approximately 1,500 bombs dropped, perhaps 200 struck within 1,000 feet of assigned aim points, roughly 13% accuracy, far below the 300-foot standard promised in training. Some bombs hit residential areas a mile from the factories. Others cratered farmland 2 miles distant. The most accurate groups achieved 600-foot circular error, double the specified performance, and still 4 times worse than training range standards. German ball bearing production declined by 38% immediately after the raid, a significant impact but far from the crippling blow planners had predicted. More troublingly, production recovered to 89% of pre-raid capacity within 5 weeks, as Germans dispersed manufacturing, imported bearings from Sweden and Switzerland, and cannibalized existing equipment to maintain production. The reasons for reduced accuracy became clear through mission debriefs and systematic analysis. Bombardiers reported that flak bursts disrupted gyroscope stabilization, requiring constant readjustment that consumed precious seconds during the final bombing run. Each nearby explosion created vibrations that threw off the carefully balanced gyroscopes, introducing errors that accumulated until the bombardier could recalibrate a process that might take 30 seconds or more. Fighter attacks forced evasive action that threw off careful tracking and made continuous target observation impossible. Smoke from earlier bomb impacts obscured aim points for follow-on aircraft, forcing bombardiers to estimate target location rather than tracking visually. Battle damage affected aircraft performance unpredictably, changing altitude and airspeed from the values input into bomb sites. Hydraulic failures, engine damage, and control surface problems all altered flight characteristics in ways that rendered pre-calculated trajectories inaccurate. Human factors compounded mechanical issues in ways that training had never fully addressed. Bombardiers suffered from oxygen deprivation at high altitude, where even properly functioning equipment sometimes delivered insufficient oxygen under stress. Cold, numbed fingers operating delicate controls, making fine adjustments difficult or impossible. Fear disrupted concentration during the final bombing run, when seconds mattered and the natural human instinct to seek safety conflicted with the professional requirement to maintain position over the target. Some bombardiers released early, unable to suppress survival instinct long enough for proper targeting. Others froze, overwhelmed by stimuli, and unable to process the information their bomb sites provided. Statistical analysis of bombing accuracy across hundreds of missions revealed patterns that fundamentally contradicted training range expectations and strategic planning assumptions. Under optimal conditions, clear weather, light opposition, experienced cruise formations achieved 600 to 800 foot circular error, roughly double the Norden's specified performance, but still respectable compared to other nations' capabilities. Under moderate combat conditions with typical opposition, accuracy declined to 1,000 to 1,200 feet. Under heavy opposition like that encountered at Schweinfurt, accuracy degraded to 1,500 feet or worse. Photographs showed bombs scattered across areas measuring thousands of feet in radius, rather than the hundreds of feet that precision doctrine required. The implications for strategic bombing doctrine proved profound and troubling. If the Norden could only achieve 1,000-foot accuracy under typical combat conditions, then surgical strikes on specific buildings became impossible. A 1,000-foot radius circle encompassed over 30 acres, an area large enough to contain dozens of buildings. Bombing a specific factory within such a circle meant accepting that surrounding structures would likely be hit as well. The moral distinction between precision bombing and area bombing began to blur when precision meant hitting the right neighborhood rather than the right building. The gap between expectation and reality forced doctrinal adjustments that moved American practice closer to British methods. Rather than single aircraft attacking individual factories using independent bomb sites, missions shifted toward formation bombing, with dozens of aircraft releasing simultaneously on signal from the lead bombardier. Only the lead bombardier actually aimed. Other crews simply dropped when they saw the lead aircraft's bombs release. The tactic increased the probability that some bombs would hit the target, even if individual accuracy suffered. It also transformed precision bombing into something resembling area bombing, saturating target zones with explosives rather than striking specific buildings. The Americans still bombed in daylight, still aimed at specific industrial targets, but the execution increasingly relied on overwhelming tonnage rather than pinpoint accuracy. By late 1943, 8th Air Force planners privately accepted that the Norden bombsight, despite its sophistication and cost, could not deliver the surgical precision promised during development. The device worked magnificently under laboratory conditions, computing trajectories with mathematical perfection that would have amazed pre-war engineers. In combat, accuracy degraded by factors of 2 to 4 depending on opposition intensity, weather conditions, and crew experience. The technology was not at fault. The Norden computed trajectories perfectly given accurate inputs. But combat introduced variables that mechanical computation could not overcome. Aircraft vibration from flak bursts, evasive maneuvers, human stress, equipment damage, weather conditions that training never fully replicated. No amount of mechanical sophistication could compensate for the fundamental gap between laboratory conditions and combat chaos. Bomber crews nevertheless developed respect bordering on superstition for their Norden bomb sites despite combat limitations. The device represented America's technological superiority, the machine that differentiated American precision from enemy barbarism, the tool that would win the war through industrial might rather than simple brutality. Bombardiers obsessively maintained their equipment, adjusting mechanisms between missions, cleaning optical elements, testing gyroscopes, performing rituals that provided psychological comfort even when objective analysis suggested the ritual's limited practical value. The belief that proper maintenance would ensure accuracy provided emotional anchor in situations where randomness and chaos determined survival more than skill or preparation. Security protocols remained absolute throughout the war, maintained with paranoid intensity even as combat experience demonstrated the Norden's limitations. Every bomber carried explosive charges wired to the bomb site, ready for instant destruction if capture seemed imminent. Crews had orders to destroy their Nordens before abandoning aircraft, using thermite grenades that would melt the device into unrecognizable slag within seconds. The paranoia proved somewhat justified when German forces recovered a few damaged but partially intact bomb sites from crashed aircraft. German optical engineers examined the captured devices with interest, finding sophisticated mechanisms but no revolutionary principles that German industry couldn't match. By that point in the war, however, the information provided little practical benefit to the Reich, which lacked resources to develop competing systems, even if the technology proved superior. The Pacific Theater presented different challenges that further exposed the gap between precision bombing theory and combat reality. Japanese targets often lay in tropical climates where clouds and storms made visual bombing difficult for extended periods. Monsoon seasons rendered entire regions unbombable for months. Distances between bases and targets pushed bombers to maximum range, leaving little fuel for extended bomb runs if initial approaches failed or weather forced route deviations. Japanese fighters proved even more aggressive than Luftwaffe opponents, attacking relentlessly through final bombing approaches with kamikaze-like determination that reflected both tactical doctrine and cultural factors. Anti-aircraft defenses, while generally lighter than German flak concentrations, still disrupted the steady flight required for Norden accuracy. Major General Curtis LeMay, commanding B-29 operations against Japan, initially attempted precision bombing using Norden bomb sites from high altitude following European theater doctrine. Results mirrored European experience: acceptable accuracy under ideal conditions, poor performance under combat stress and weather interference. Reconnaissance photographs of strikes against Japanese aircraft factories and steel mills showed scattered bomb patterns distressingly similar to those over Germany. Some bombs struck targets. Many more fell on surrounding areas, destroying residential neighborhoods while missing intended industrial facilities. The moral distinction that justified precision bombing over area attacks eroded when precision proved impossible to achieve consistently. LeMay's solution revolutionized the Pacific Air War, while effectively abandoning the precision bombing doctrine that the Norden represented and that had justified America's enormous investment in bomb site technology. In March 1945, he ordered B-29 seconds to conduct low-altitude incendiary attacks against Japanese cities at night. The new tactics explicitly rejected precision in favor of area destruction designed to burn out industrial districts and the workers who staffed them. Bombardiers still used their Norden bomb sites, but for the crude task of bombing residential districts rather than specific factories. The device, capable of theoretical 300-foot accuracy, was employed to hit targets measured in square miles. The $8,000 mechanical computer that represented the peak of analog technology was reduced to simple navigation equivalent to using a Rolls-Royce for grocery shopping. The firebombing of Tokyo on the night of March 9 and Teenage 1945 demonstrated the new approach and effectively marked the end of precision bombing doctrine in the Pacific. 334 B-29 seconds dropped 1,665 tons of incendiary bombs across residential districts, creating firestorms that killed over 100,000 people and destroyed 16 square miles of the city. Bombardiers used their Norden sights to aim at general areas rather than specific buildings, identifying neighborhoods rather than factories. The mission succeeded not through precision, but through overwhelming destructive power applied indiscriminately across entire neighborhoods. The distinction between this and German terror bombing of London or Rotterdam became semantic rather than substantial. The strategic shift represented complete abandonment of the doctrine that had justified the Norden's development, the billion-dollar investment in production and training, and the moral superiority that Americans claimed over British area bombing methods. American bombing in the Pacific became functionally indistinguishable from British area bombing over Germany, deliberate destruction of civilian areas to undermine enemy morale and industrial capacity. The expensive, sophisticated, closely guarded bomb site designed for surgical strikes was relegated to approximate navigation rather than precision targeting. Nobody court-martialed LeMay for effectively discarding precision bombing doctrine because results mattered more than methods, and burning Japanese cities produced results that precision strikes on specific factories had not achieved. Post-war assessment teams examining bombed German and Japanese facilities documented the gap between precision bombing theory and practice with mathematical precision that made uncomfortable reading for those who had promoted the doctrine. Bomb damage surveys in Germany revealed that of roughly 2.7 million tons of bombs dropped on Europe, Approximately 900,000 tons struck within 1,000 feet of intended aim points, roughly 33% accuracy, measured generously. The remaining two-thirds fell on unintended targets, empty countryside, or areas so far from aim points that their impact on military objectives was purely incidental. Strategic targets like ball-bearing factories, synthetic oil refineries, and aircraft plants suffered significant damage, but from cumulative tonnage rather than precise targeting. German war production continued increasing until late 1944, not because bombing proved ineffective, but because precision doctrine overestimated the Nordens' combat capability and underestimated Germany's capacity to disperse production and repair damage. Japan's Strategic Bombing Survey reached similar conclusions about Pacific operations, expressed with the careful diplomatic language appropriate for official documents that would be politically sensitive. High-altitude precision attacks achieved limited effectiveness against point targets, rarely destroying specific facilities unless multiple raids concentrated overwhelming force. Low-altitude area attacks destroyed Japanese cities efficiently, but abandoned any pretense of precision or moral distinction from enemy methods. The survey noted that the Norden bomb sight, while technically sophisticated, could not overcome the fundamental challenges of visual bombing in combat conditions, weather, defenses, human factors, and mechanical limitations that no amount of engineering could eliminate. The cost analysis proved sobering for those who examined the numbers honestly. America had invested over $1.5 billion in developing and producing more than 50,000 Norden bomb sites at roughly $8,000 each, nearly $400 million in direct equipment costs alone. Training programs consumed additional hundreds of millions in facilities, instructors, aircraft time, and practice munitions. Security measures guards, special storage facilities, classified procedures, explosive self-destruct mechanisms added tens of millions more. The total investment exceeded the Manhattan Project's costs through 1944, making the Norden one of the most expensive weapons programs in American history. Yet combat accuracy rarely exceeded 50% of specified performance, and often fell far below that standard. The return on investment looked questionable when measured purely by technical performance against specifications. The broader strategic impact remained more difficult to quantify. Strategic bombing unquestionably damaged German and Japanese war production, destroyed enemy air forces through attrition, diverted enormous resources to defense that might have been used offensively, and contributed to final victory in ways both tangible and intangible. Whether this justified the enormous costs in resources, aircraft, and crew casualties remained debatable among historians and analysts. What seemed clear was that precision bombing, as originally conceived and promised by Norden bomb sight advocates, had proved impossible given the technological limitations of the era and the realities of combat operations. The Norden bomb sight succeeded magnificently at its intended task, computing bomb trajectories with unprecedented precision, using purely mechanical means that represented the peak of analog computer technology. Where it failed was in the assumptions underlying precision bombing doctrine. That laboratory accuracy would translate to combat effectiveness, that visual bombing could consistently identify and strike small targets from high altitude, that bomber formations could maintain steady flight long enough for accurate bombing, despite enemy opposition, that human operators could perform complex procedures under combat stress with reliability approaching peacetime training. These assumptions proved optimistic at best, fantasy at worst, when confronted with the friction of actual war. German technology told a parallel story of optical precision confronting combat reality, in ways that suggested the problem transcended national capabilities or engineering approaches. The Luftwaffe's Lot-Fernrohr 7 bomb sight, developed independently using different mechanisms, achieved similar accuracy to the Norden under ideal conditions. Combat degraded its performance identically for the same reasons: human factors, weather interference, defensive fire, equipment limitations. Britain's Mark 14 bombsight likewise demonstrated excellent test range accuracy and mediocre combat results. The problem was not unique to American technology or to the Norden specifically. All visual bomb sights of the era faced identical challenges that mechanical sophistication could not overcome, suggesting that the limitations were fundamental rather than correctable through better engineering. The nuclear missions against Hiroshima and Nagasaki in August 1945 demonstrated both the Norden's capability under ideal conditions and the role of chance in combat operations regardless of technology. The B-29 seconds Enola Gay and Boxcar carried Norden bomb sights for aiming the atomic weapons, with the ironic result that humanity's most powerful weapons were delivered using the same technology that had proven inconsistent against conventional targets. Clear weather and zero opposition allowed bombardiers Major Thomas Farraby and Captain Kermit Behan to conduct textbook bombing runs free from the stresses that degraded normal combat performance. Farraby's weapon struck approximately 800 feet from the intended aim point over Hiroshima, respectable accuracy under any standard, but still nearly triple the circular error that training had promised. Behan's bomb fell nearly 6,000 feet off target at Nagasaki, due to last-second visual acquisition of the secondary aim point through clouds after weather-forced abandonment of the primary target. Even these most critical missions in history demonstrated the gap between theoretical precision and actual performance, though the weapon's enormous destructive radius made pinpoint accuracy unnecessary. The lessons shaped military development for decades, influencing everything from guided munitions to modern precision strike doctrine. Post-war analysis teams attempted to quantify what had worked and what had failed, producing recommendations that acknowledged uncomfortable truths about technology's limits. Precision-guided munitions developed after the war accepted that human operators could not consistently achieve accuracy in combat conditions, and therefore automated tasks that proved beyond human capability under stress. Radar bombing sites eliminated dependence on visual identification, though early systems offered crude accuracy compared to optical methods. Later laser guidance, and eventually GPS navigation, automated more of the targeting chain, removing human judgment from calculations where stress and fear degraded performance. The Norden represented the peak of what mechanical computation and human operators could achieve together. Subsequent systems acknowledged that peak was insufficient and required electronic computation and autonomous guidance that the 1940s could not provide. By 1946, the veil of secrecy surrounding the Norden lifted as the device's strategic importance evaporated with the war's end. Surplus bomb sites filled warehouses, deemed obsolete by the jet age and guided weapons already under development. The device that had been more closely guarded than radar technology, that required armed guards and destruction charges, that represented 5-year technological advantage over enemies, became museum pieces and training aids almost overnight. Technical manuals, once classified above top secret, became publicly available, revealing no revolutionary principles, that security had protected only sophisticated execution of mechanical computation that any competent engineer could understand. The most secret weapon in the American arsenal joined thousands of other wartime technologies rendered obsolete by rapid post-war advancement and changing military requirements. Surviving Norden bomb sites rest in aviation museums across America today, polished mechanical marvels that visitors can examine through protective glass while reading plaques describing the device that won the war through unprecedented accuracy. The museum displays rarely mention that combat accuracy averaged 4 times worse than specifications, that doctrine based on the technology proved impossible to execute as planned, or that the most expensive bomb site in history ended its service career aiming incendiary attacks at residential neighborhoods. The more complete truth, documented in thousands of pages of post-war analysis that few read, is that the Norden represented advanced technology, confronting the eternal friction of combat, where laboratory perfection meets human fear, mechanical failure, weather, and chaos beyond any engineer's prediction or control. The statistics tell the final story with numerical precision that avoids value judgments. Over 50,000 Norden bomb sites produced at a cost exceeding $400 million. More than 50,000 bombardiers trained in their use at costs reaching into billions when facilities, aircraft, and support personnel are included. Nearly 3 million tons of bombs aimed through Norden optics over Europe and Asia. Circular error probable in training. 300 feet under ideal conditions. Circular error in combat. 1,200 feet average under typical conditions, often far worse under heavy opposition or poor weather. The most sophisticated analog computer of the Second World War delivered accuracy sufficient for strategic effect when applied in overwhelming quantity, but far short of the surgical precision that had justified the technology's development and the doctrine built around it. On September 12, 1944, First Lieutenant Robert Morgan released his bombs over Schweinfurt and watched them fall toward the factories below. Trusting that the Norden bomb site had computed the trajectory perfectly and that his aim would prove true, his Norden had indeed computed perfectly, accounting for altitude, airspeed, wind drift, and ballistics with mechanical precision that human calculation could never match. The bomb struck nearly 1,000 feet from his aim point, not because the device failed its mathematical task, but because combat forced compromises that training never anticipated and technology alone could not overcome. The gap between technology's promise and warfare's reality defined precision bombing for an entire generation, until electronics and autonomous guidance finally delivered the accuracy that mechanical genius, for all its sophistication, could not achieve against the friction of actual war. If you value fact-based history that reveals the gap between technological promise and combat reality, consider supporting this channel.